This is Bill Foote, and this is Stats 1, and we are nearly at the end of our journey together. This is Lecture 12, Relationships. Well, the relationships we're talking about are those that have associations. And the example I want to use is an oil refinery. This is going to be important to understand in terms of the technology involved, climate change, pricing, availability. All sorts of questions are going to be coming up. And we might want to know, what is the relationship of input and output at a place like a refinery? Now, if we do that, we might begin to think about this relationship, which we start at the fence of such a refinery, maybe perhaps in Linden, New Jersey, for example. And at this fence, there's a great big oil pipe that comes in. And there it is. Okay, and there's a measurement at that fence with that pipe. There's a hole there for the pipe to go through. You've got to imagine this, and the pipe carries crude oil all the way from West Texas, and that's called West Texas Intermediate. Around the Katy area, the Midlands area of Texas, Permian Basin is near there. And this, the technology that's been running off of crude oil hydrocarbons for the longest time, many decades, going back at least 120 years now, is the dominant technology, and it's being taken over by another technology. One that everyone says is quite a bit more sensitive to climate change, electric cars, for example. And we can have exactly the same kind of model, electric cars, different input, different output. So at the fence, say at Linden, New Jersey, this happened. Now, what's at Linden, New Jersey? Well, it's basically a great big refinery run by a bunch of very dedicated people, especially with safety in mind. It's called a refinery. And these are the places where the refining occurs. The West Texas Intermediate molecules are cooked. And each one of these has kind of like a stack inside of it, a cooking stack. The bottom of the stack is asphalt for our road, as opposed to concrete. Asphalt's more flexible, certainly better for high volatility in temperatures and humidity, as well as the type of terrain. Interesting. That's all made out of crude oil. Now, what comes back out is another pipe. If I can draw it here, maybe several other pipes, and another fence. It's all measured out. The one we're going to be interested in is unleaded gasoline. Just 87 octane, all right? We'll leave it at that. Now, between WTI and UNL, there's a spread, which is UNL is going to be measured in dollars per gallon. And WTI, let's put a circle around that, measured in dollars per barrel. Our first measurement task, BBL for barrel, is, well, we can't compare gallons and barrels directly. That's not a possibility. So what are we going to do? create a little bit more real estate here. We need to convert UNL into dollars per gallon. Now, in order to do that, we take whatever the UNL might be, $4 a gallon, for example, multiply it by some other number, which will be gallons per barrel. That's a conversion factor. Of course, most everybody knows this. And certainly for the US system of weights and measures, in this case, volumes, a barrel is 42 gallons. Please look that up. Okay. So when we do that, gallons in the dimensional analysis, gallons to gallons is equal to 1 dimensionally. And so what we then get is UNL, just take 42 gallons per barrel and multiply it times the gasoline price. Okay, we get dollars per barrel. So just to try this quickly, if gasoline is $4 per gallon, we multiply this times 2, we get $168 per barrel. And if West Texas crude is $50, $60 a barrel, the spread will be $1.68 per barrel minus whatever West Texas crude is. Suppose it's $60 per barrel at this moment. So the spread, which is a measure of the activity inside of the refinery, delivery to a demand, arrival of a supply input, it's the spread. And in this case, the spread would be equal to per barrel, 60 minus $108. That's quite a spread, huh? So is that refinery worth $108 per barrel? In a sense, yeah. There's more to it than that. How many barrels going to produce in a year? That gives you an idea of how much that refinery is worth in a year. And then if we track that, given the ups and downs of gasoline prices and WTI prices, because they're going to vary all over the place, gasoline might look like this. Well, WTI might look like this. Much less volatile. Again, in order to compare these two, you have to be in dollars per barrel. The dimensions have to be comparable. Okay. Got that idea out of the way. Now, the present value of all those future spreads, discounted by the amount of risk inside of this. Now, there's technological risk, certainly. There's operating risk. There are fires in refineries all the time. There is the riskiness of this input and this output. So we have a number of risks that would need to be compensated for. The idea of finance, anyways, and some sort of financial equilibrium. Investors would want to be compensated for risk. They might also want to be compensated not just for the marginal risk, but also for the accumulated risk. Just as in probability, we sometimes move to the cumulative distribution function as opposed to what we see right here, which are simply the marginal distribution. Sorry, probability distribution functions. Already thinking ahead. Okay, so now, if we have all of that going on, which is quite a bit right now, back up here, here's our technology, stuff going in, being transformed into stuff going out. I didn't show the truck that was there. This area here is called the rack. Gasoline and other distillate products are delivered to a rack and then put on trucks, and then somehow they get through the neighborhoods, okay, to your local station. That difference is that spread. Now, the key thing to remember is it has to be on an equivalent basis. You got to be comparable. No gallons and barrels. It has to be barrels to barrels, dollars to barrels. Okay. Now, it so happens that the functional currency in this market, almost worldwide, not quite, but almost worldwide, is in dollars. Relationship between Russian crude going over, which are in rubles, and going over into China to be refined in yuan, creates its own, effectively because of the strength of the trade, creates essentially something, economically speaking, if not juridically, but it looks yes, like a contract going on there across that border is something like a currency unit. So these any global events that affect that will affect this eventually here in Bayonne, New Jersey, or any other place where a lot of refinery is. Okay. Hawaii, Alaska North Slope. All right, so we have all of that, and Japan is affected by that. Okay, so everything is kind of moving together. Okay, not just one big system. It's highly interconnected. All right, so what do we want to do here? We want to relate. Typically, what we want to do is relate spread to the input. You can do a very rudimentary market spillover analysis. How does the WTI market, supply and demand, all the forces there, and all the technologies therein, how does that spill over into the unleaded gas market? It does so by way of the spread. It's very, very. There's other ways of doing this where we would take a rolling standard deviation of WTI and look at how that impacts a rolling correlation of WTI to unleaded gas. I mean, that's an interesting story to tell. That's a market spillover, but this one will work very fine right here. So we might see, for example, a scatter plot, something we all have known at least since 6th grade. A scatter plot, those aren't sixes, those are just little badly made drawn points. A scatter plot of spread versus WTI. Well, that would mean that we had a table over here of WTI prices and spreads. Now, for example, as in this table. Here are the spreads, and you can see what the formula is. The unleaded gas, which is in dollars per gallon, minus 42. The answer is always 42. Hitchhiker Guide to the Galaxy, Douglas Adams, thank you very much, times D3. And if we look over here, we do have named ranges for these. We have the spread, that's the spread. also called crack. Oh, lovely. And WTI. We can, if we want, insert some sort of, well, that's just a WTI movement. That's kind of interesting in and of itself. And just put a chart title. That little phrase there. See if I can snag it. There we go. Let's just give it some help here. You can also go up here to design, chart design, and do a select data. And don't give this a name. You don't have to do that. I never do that. I always do this. Take the series name, and I'll just take it as spread for the moment, with x-axis values, WTI. The y-axis values. Notice how I got rid of that one there. Spread. And say okay. Now let's see what happened here. Series 1 point. Series 2 spread. Okay. This didn't work so well. Let's see what happened. And that happens. Select data. Oh, we have a series here. We don't want to have that series in there at all. So we remove it. You see it did a nice overlay of the two. Okay. Now we can further take this. Let's just zoom this in a little bit. Right click on that field. Let's pick 30 on the x-axis. There we go, just to make things a little bit easier to see. Get rid of my fudge there. And there we go. There's a relationship between these. It looks a little bit like it's upward sloping. And let's just click on one of those points in the scatter plot, right click. Okay, right, format. Add trend line is the thing I'm looking for. You can actually put a trend line in there. You can see it's already popping in there. Also going to, something else we can do is we can display the equation of that straight line. You can also do something else called R squared, which is a very interesting descriptive statistic we can play with. Those, let's bring this down over here. We're going to need to look at those at some point. So the R squared basically says if we were to draw little lines, deviation lines from the point to the line, vertically. Okay, R squared would be some notion of the percent of variation in y, which is spread here. What percent of the variation in spread is accounted for? So nothing else, no inference, accounted for by WTI, which is on the horizontal axis. I didn't put any axes in here. It's 68%. They're pretty well aligned with one another, and the 22 ends up being an intercept. Now you got to remember this goes all the way to 0, and 0.5527 ends up being the slope, the rise over the run. So that is all going to be measured in dollars per barrel. It's $55 per barrel spread change, it's an impact for every dollar of WTI increase. You do see that rise over run, and that would be the interpretation. If there's a $1 increase in WTI dollars per barrel, there will be a little bit over a $0.50 increase in the spread. The 22 is also interesting. If WTI were free, this is an intercept. If WTI were free, the spread would be $22. As WTI goes up, the spread rises. See, we get, and that shows the upward slope. But the spread here, for example, for a WTI of $83, I'm sorry, of $62, the spread is $81. That's how high gasoline gets. Now the question is, does the spread increase, and why? Why does the spread increase is the question. And the answer to that might be the same as the core fiber answer. High prices might be gouging on the one hand. And so we would want to identify high prices as opposed to low prices, high spreads as opposed to low spreads. What's a refinery doing? It's creating value, no question. It's transforming a product like crude oil into another product called gasoline. And it's unleaded gasoline. There's a lot of chemical processes going on there. There's a technology to pay for and to keep improving and to keep from blowing up. Insurance, funding of the operation, the credentialing of employees, the management day to day, month to month, year to year of that facility, taxes being paid. All of these things would contribute to spread, would have to contribute to spread. Storage, lack of storage, the risk of not having enough crude to go through the plant and satisfy demand. That's a risk. So we have all of those things going on inside of the spread. Going back to the picture show, there we go. We have here, there we go. And here's the $22 per barrel intercept, y-intercept. Remember, that's 0. WTI, I like everything 0. But suppose somebody paid for it. All right, there we go, 0 to you, $22 per barrel. And then we have the rise of 0.55. And again, always remember the dimensions, because that will be your interpretation. And it takes it from the realm of math, which will work every time with this system, this approach, these assumptions, every single time, into what does the math mean? How do you interpret it? What's the key by which you interpret this? And the key for this is the physical technology and its management as a business, or as a sub-business of a larger business, or as a facility located in 2 markets. There's actually the 3rd market, which is the market for the capital, and the employees is a 4th market, and the corporate control of all of the facilities is a 5th market. Okay, thinking about it from a market point of view. $55. So if you have a $1 increase per barrel of WTI, you get a 55-cent dollars per barrel spread facility. And that is the degree of, now you want to compare this with other facilities, other markets, and so on and so forth. right? So that's the basic interpretation. How do we get the 55? How do we get the 22? Well, let's look at how that might happen. And before I do that, let's go to the source of all of these with all of this discussion, which is chapter 11, which uses two different examples than what I'm using here in the lecture. One example is the simple model, as you can see here, where you have the intercept and a slope, where A only takes on the binary value of 0 and 1. If A equals 1, mu equals alpha plus beta. If A equals 0, mu only equals alpha. This kind of gives you a test, an interesting test. Which model would you want? It would depend upon the circumstances of the observations of the data. Circumstances. It's called efficient causality, by the way, in the causality approach. And mu given A equals 0 is A or alpha. Mu given A equals 1, alpha plus beta. Very, very useful example. Do check it out. And one of them will occur with a probability and the other occur with the other probability. The ratio of those probabilities are the odds. The log ratio is actually called the information, but we won't go into that here. Okay. And here's a hypothesis test, very similar to a lecture 11, where now we have to specify the value of A. And we're going to do something very similar with WTI. Very, very similar. So we have, in this case, one situation, PM, post-meridian, ante-meridian, morning, afternoon, and we get two different probabilities. One, it seems to be favoring just the morning. A equals 0 model. Well, what is that? The wait time in this particular model is 3 minutes. So in this customer service model, which is very similar model, input, output, y-intercept, rise over run is B, all right, you get the same senses of what we're doing, but this is a much simpler model. Okay, and here's a lovely little picture of the whole thing. And we get this notion that this is going to be wages and education in this. Now I take a digression here on the maths. Okay, what we're going to do is say we have a probability and we have outcomes. What is the expected outcome? It's the weighted average. Probability are the weights, and we did this already way back, and that was the expectation. And we're going to use this notion of P being an operator, an expectations operator, where the operation is take any value of Y, and it's the sum product of that value of Y with its associated probability. The information we have about Y is literally encased in its probability, not just the value of Y anymore. And this is the way that this works. And I'm not going to go over this here. I might pull together another broadcast, but read through it. It's algebra. Okay, just pure algebra. You go through the pure algebra and realizing that probabilities add up to 1, you get all sorts of interesting results with this operator approach, which is very much the approach favored, certainly in the statistical physics and in algebraic, something called algebraic geometry, and differential geometry as well, which is the underpinning of a lot of so-called data, so-called science of data. I guess that's what that means, but neither here nor there. And we can compute, for example, if we have a product. Now we know where the products come from things like variance. That's where this is going. What is the expectation of product of two outcomes, each with probabilities. Okay. Expressions like that, and then get this. So suppose y equals x, and then we have the product is, oh, the square. Oh my goodness, yeah. Expectations of squares. And we use all of these things in order to build this sort of idea. X, y being alpha this and alpha that. It is logic. And then we use more logic to calculate things like the covariance. Then solving for that A and B, that's just simultaneous equations and so on. We can go through all of that, but what I want you to get down to is the expectation of spread, which is y, given WTI, which is x, is equal to the intercept plus the slope times the expectation, or the average of WTI. That's what we're going to use. But it makes kind of makes sense. And we can do the covariance very similarly and get a way to think about that as well, and calculate effectively what that 0.55 was. How it actually gets calculated is there's a covariance in the numerator divided by the variance of WTI in our case. That's the ratio that will matter. We can also convert that ratio into correlation. I mean, you're doing this, you got your pencil out, of course, the gnarly maths, yeah. If correlation is defined as this relationship, as it is, then solving for sigma xy, the covariance, and covariance is equal to the correlation times the product of the standard deviations. You're going to see this in places like finance and portfolio. Thus, taking the definition of beta 0.55, remember in our WTI spread example, we come down to this expression, rho, which is correlation, which is what most human beings use, times the ratio of the risks of spread versus WTI. It has a way to think about it. Okay, that's the point. And then there's a diatribe I go through. Oh, look at this. This is the standard deviation of the spread given WTI. And there's a correlation. It's basically discounting the spread risk. Okay, that's the idea here. So we'll look at that in a second. And then here's the rest of the story. Oh, you see here again another upward slope. This time with a negative, which totally nonsensical in this wages education case, instead of spread and WTI. And then all of the rest of this over here, and then we get back to the business at hand. Okay, and calculate things. So the typical thing is you want to get to a panel like this where you have the mean and standard deviation of spread, the mean and standard deviation of WTI, so wages education, and you get their correlation. And you can get those pretty easily just using standard, as you can see in M. Standard approaches to their calculation in Excel in this particular case, in the spreadsheet. And then you do the rest of the calculations and notice that these calculations line up exactly with that trend line. That's kind of a check on our work. And then in another part, what we will do is this with the WTI. We will, instead of A being 1 and 0 for AM and PM above this, we now have two different educational levels, college and high school. And we asked the question, wage of $18.20 is, well, is it a college wage or a high school wage? It turns out that the odds are exactly the same. Okay. They both have the same sigma. And mu is equal to alpha plus beta times 16. The other one is alpha plus beta times 12 to get to 25 and 10. Those are dollars per hour. Again, keeping the dimensions straight in our minds. And does it really matter? Well, we can go into that as well, but just keeping up with this is enough for me. I want to pick which model is better, the college model or the high school model for that wage. Right now, we'd have to flip a coin, and we wouldn't know because the odds are the same. Okay, so 1-to-1 odds, 1-to-1 probability, given high school or given college. Probabilities are the same. All right, now getting back to this, where the heck were we? Well, there's a refinery, there's the spread, there's the conversion of gallons to barrels. Here we are, $22 and 0.55. Okay, we have WTI, we have spread, we have these numbers, and our model is this. Now, what is sigma? And that's what we would have to compute. But sigma ends up being whatever happens to be the correlation, which happens to be 0.66. And I've already forgotten. Let's go back to the spreadsheet just to see what that number was. Sigma spread is 7.65. Notice the spread, the standard deviation of WTI is $11, and the spread is 7. It's less, absolutely less. We'll make something out of that. So knowing that, we just go back and draw the picture, which is all we really need. 7 and gee, I've already forgotten. What's the matter with me? Okay. 7 and 11. There we go. Almost $8. We'll call it 8 and 11. All right, just for illustration purposes. So this will be times roughly 8, 7 and change. I mean, when we think about this, and we should be thinking about it, it looks like this. The spread is like this, and WTI is like that. Why? No, it's just that way, but think about the difference. The spread is not as volatile as the WTI. Okay, spread is not as volatile. So what ends up happening, the model sigma, which is that sigma right there, which takes into account the relationship between spread and WTI. That's the what? Correlation. Just putting this. That's for spread. Deviation of 8 already taking a discount. 1 minus 0.66 squared, all right? 0.66 times 0.66. 0.6 is 0.03 something, 0.02 something, right? Squared. 1 minus 0.02 is, okay, it's like a 98% of 8. That's the idea behind it. How could that be, you ask? Well, just look up here for a second. Those variations are these. Where the sigma comes from. The vertical lines here. And each one of those deviations, sum them up, square, ends up being the sigma that we're looking for. And we're also assuming that given this mean, which varies with WTI, that's the key, and that's what we're going to do in the next round here, that variation in this model, which is being captured exactly by sigma, constant, the constant variation, and it is normally distributed. And that's what we came up with down here. We have the mean and we have a standard deviation. So we actually have the model right here. That's input into this model. The model is, in a sense, a higher order systematization of WTI and spread interact, because it allows us to say, what is the average relationship mu? But not only that, it isn't mu and it's off mu. The observations were off mu. Those vertical lines show that's the scatter plots. They're not on the line. Some might be close. Then we also have more information about how they're related by how they're not related. So we have a model of how they're related, and the sigma tells us the degree to which they're not related. That's extremely important. And the sigma, again, 1 sigma down, 1 sigma up from the mean. The mean is going to move for every single value of WTI, remember. The mean moves. No longer sitting still. It's moving. And at the point of inflection of this Gaussian curve, it switches over from rising slowly to rising much more quickly and dropping quickly and then dropping not so quickly. That point of inflection is 1 standard deviation. 67% of the probability is somehow in between those two. As a rule of thumb, and this is why people love the Gaussian normal curve, got all these rules of thumb, but it's very unrealistic. It's only realistic in highly, highly rarefied situations. But back of the envelope, back of the envelope, if you like, X of the envelope and knee-jerk reaction to whatever. No, not quite. It's more than a knee-jerk reaction. Okay. Gives you an idea of how things are related. Okay, it passes the common sense test of, yeah, WTI is somehow in its relationship to spread, kind of like attenuated, calmed down a little bit. There we go, calmed down a little bit. What does sigma cost out to? $2. It's $2. Taking into account 22.55, but mostly the 0.55 piece. Okay, and that comes, the spread here is 82. Oh, my apologies. Let's get back here. $2. Very little discount. There we go. We'll go back to those calculations in part 2 and realize how we can go from there to hypothesis testing directly and choose a model. The whole point of this is ultimately model choice. Hypothesis testing for me has always been model choice. I choose one over the other based on the odds. And now that's not the end of my decision making. All I can say is one model is better than the other, compatible with the data and our assumptions about how we observe that data and mash our assumptions or theories or conjectures, or what else we call them, hypotheses, with the data. Matching hypotheses and data. Okay, so we will come back to that. Let me pull the refinery back up here. Okay, and maybe we can find Linden, New Jersey. Refineries. Oh, they got an Exxon and Hess. Those are the two big ones. Yeah. Right off the highway. There we go. There's a refinery. Here's a refinery. CO2 going up there. Typically, that's CO2. Tank farms in the back. It's just an awful lot. What page this is on? Oh, these are just Getty images. Here's the tank farms right here. Look at that. Nice panoramic view. Lovely. Love that kind of a clip. Cars going by, that's a Jersey Turnpike. Those are evaporators, more evaporators, more evaporators. All right. Oh, and there are the trees. Wonderful. Thank you for that. Anyways, I'm going to leave you with this, and we'll be coming back to this problem with WTI. Take care, and thank you very much for your kind attention.